Okay, perfect. Thank you very much for inviting me. So I'm going to be talking about the complexity of approximate counting. And this is basically designed to be a little bit of a survey because I think I'm kind of in a somewhat peripheral area, although actually much more connected than I thought, as I learned yesterday. And but really, we're about generating functions, but actually evaluating them and approximately evaluating them rather than coefficients and things. And some of the techniques are a little different. So I'll get to some recent work at the end and more just trying to give you a flavor. And I love interruptions and questions at every point since that's actually the point. So feel free. Okay, so to start with the warm-up, I just thought I'd tell you what, so we're going to be talking about different generating functions. And I thought I'd just give you a feel for the sorts of partition functions or sums of products that we're looking at. And they're mostly motivated by statistical physics, so we know all of them. But I'm going to start with the independence polynomial, which I think is quite familiar, and we'll just give you a kind of vibe for what sorts of things we're looking at. Okay, so we've got a graph. Oh, that doesn't even work. Well, never mind. That's fine. So we've got a graph G, and we know what an independent set is. Set of vertices has no edges. And so I've just drawn a picture here of the independent sets of G, and we're going to make a polynomial out of them. So there's an independent set with no vertices, or obviously any of the sets with one vertex is independent, or so on. And I've just enumerated the independent sets of this particular graph. Okay, so the independence polynomial has a parameter lambda, and it's just the sum over all independent sets in the graph of lambda times to the number of vertices in the independent set. So I sub G is just the set of independent sets. And so for this particular little graph, the independence polynomial is this, because I've got one independent set with no vertices, I've got 5 independent sets with 1, 5 with 2, and so on. Okay, so that's the polynomial. And we're interested typically in approximating this polynomial at a value lambda. And you can see that obviously it would take a long time to just enumerate the independent sets, because normally we've got a big graph. So there might be 2 to the n. If you've got n vertices, there might be 2 to the n terms. So we don't want to do that. But we want some faster way to evaluate or to estimate the polynomial for a given value lambda. And of course, if you take lambda 1, it's just the number of independent sets. Okay.
Some significance of other values of lambda? Why?
Well, okay, so that's a great question. So why would we care about other values of lambda? And if you press me hard, eventually I'll get bad at answering the why, but this one I can do. So the physicists have something called the hardcore model. And it's a model of a gas that lives on a lattice. So the graph is the lattice. And the vertices can be occupied or not occupied by particles. And the idea is that the particles have mass. And they can't, on an edge, you just can't have 2 of them, because they take up too much room. And lambda tells you about, let me just say energy coming from the particle. It's not really energy, but okay, so it's physics model, and they're interested in other lambdas, therefore. Good. Okay, and so we're interested in estimating this polynomial. But really, the reason we're interested in estimating it is that we're interested in sampling. And actually, that question was super helpful, because why would we be interested in sampling? Because we might be interested in what's a typical state look like. So you want to draw a sample and see what it looks like. And so we're going to sample from the Gibbs distribution. And I think Cyril yesterday was very careful to define the Gibbs distribution in a way that's different from the Boltzmann distribution. But let me just say that for me, these are absolute synonyms. And there's no single difference in our world. So, so the Gibbs measure, or for me, the Boltzmann measure, is a measure on independent sets where the probability of a particular independent set is just proportional to lambda to its size. So to its own weight. What does it contribute to the polynomial? So for example, this little example here, the picture I've drawn with these 2, the weight of this configuration is lambda squared. So its probability is lambda squared divided by the partition function. And we saw yesterday why the partition function was called Z, because it's a German word that starts with Z. But anyway, okay, but the partition function is just the normalizing factor in this Gibbs distribution. So we want to sample from this distribution. Okay, so we start out by asking how hard it is to actually compute the independence polynomial for a fixed lambda. The physicists call the lambdas activities, so I might do that because I've been around their world for a while. But let's start with lambda equals 1. So now we're just counting independent sets. And we've known since, well, I didn't know it in 1979, but Les Valiant certainly did, that this problem is actually number P complete, which is really as hard as you can get for these types of problems. And that's true even if the graph is cubic. So we don't have any hope of actually computing the number of independent sets. And so that's a hard problem. And of course, there are hardness results for other values of lambda too, but I'm just going to start with lambda equals 1 there. But most people are more interested in approximating the partition function, because if you wanted to sample, apart from the kind of theoretical interest, which certainly it is interesting, you don't actually need to evaluate it exactly. So that's why we're interested in approximating it. And when we talk about approximating it, we need to think about how well should we approximate it. So the usual setup is that you fix the parameter lambda, and then you're interested in a setting where the input is the graph, but the input also has an accuracy parameter epsilon. And the name of the game is you're supposed to spit out a value, which I've called z hat. And z hat doesn't have to be exactly the value of the partition function z, but it should be within 1 plus or minus epsilon. So within a factor of 1 plus epsilon, 1 minus epsilon. And the idea is that the running time should be a polynomial in n, the number of vertices in the graph, but also a polynomial in 1 over epsilon. And so as we demand more and more accuracy, you're allowed more and more time, but not arbitrarily so. So this is called an FPTAS, a fully polynomial time approximation scheme because it applies to different epsilon. Fully because we have to be polynomial in 1 over epsilon. FPRAS is if you're allowed randomness. Now you might think, wow, well, if you don't work in this area, what a kind of hokey and kind of overly convoluted definition. And if you think that, you don't have to care about this definition, because for everything that I'm going to tell you about, if there's an FPTAS, yay, you can approximate so well like that. And if there's not, then it'll be easy to prove you can't approximate within any polynomial factor. Okay, so honestly, the thing's super robust, and if you think that's just too demanding, then ignore it. Think about a factor of 2 or whatever you like, because and it's easy to kind of see that in this case. And just to give you, if you haven't come across this before, the reason for it is that if you suppose you could approximate within some bad factor, like a factor of 100, what you could do is you could take a bunch of copies of the graph, and then you would be able to power up to and get this close approximation. So we don't really have to worry about the details of the definition. And so given that, the question is when, and when is there a good approximation in the sense of FPTAS or FPRAS? And when I mean for which parameters lambda, and also for which families of graph. Okay, so that's the basic setup question. Make sense? Okay, now, it turns out that by now, we know a lot about this, but annoyingly, for you probably, in order to tell you about it, it's helpful to add more parameters. So it's helpful even if you don't care about bounded degree graphs. It's helpful to walk through bounded degree graphs, because if we want to discover the truth about this problem, we have to go through that. So I'm going to let G delta be the set of graphs with degree at most delta. And then I'll be able to tell you what was really a big discovery in the field around 2010. And That's that there's a critical value, lambda critical, which is, you can, I mean, I've written the exact value in case you care, but it's about E over delta as delta gets big. And it turns out that, let's look at the problem of approximating the partition function on the set of graphs of degree at most delta. Now, we'll be able eventually to take delta equals infinity. I mean, if you like, in a better sense, you're not going to like to do that right there, but don't worry about it. But for now, let's just fix delta. And let me ask, can we approximate the partition function when the input is an arbitrary graph of degree delta? And the truth is that if lambda is less than this critical value, then you can do that. You can approximate in the best possible sense. So there's an FP test. So there's a deterministic approximation algorithm that gets you as close as you want. And on the other hand, if lambda is bigger than this critical value, then actually, even if you just restrict yourself to delta regular graphs, and even if you only want to approximate within an exponentially bad factor, that's just impossible. Okay, so this critical value is really the truth between when you can approximate. And it's possible to really understand and to make sense of this critical value and why it is that, you know, approximation is easy below that and hard afterwards. So I want to tell you a little bit about that next. So in order to do that, what I want to do is I want to, we're interested in approximating on general graphs of degree delta, but we're going to take a little detour and look at trees, because all of the truth about the hardness for these values can be captured by what's going on with regular trees. So first, I'm going to let Z in V. So I've just added some decorations to this polynomial. So I had the partition function, and now I fixed a vertex V at the bottom, and I've put a decoration on the top. And that's just to tell you that this notation here that I can't point at is the contribution to the partition function coming from independent sets where V is in. Okay, so that's part of the partition function. It's the sum over every independent set containing V of its contribution. Okay, so in that case, I can define P sub V, which is just for any vertex V in the graph, just to be the probability that V is in the Gibbs measure. So just the contribution from Vn divided by the whole partition function. And now what I want to do is I want to look at a delta regular tree of some height h, and I want to think about the root. And I want to think about what's the probability that the root is in when I look at the Gibbs measure on this tree. Okay, so I'm going to, sorry for all the notation, but therefore I'm going to define P of h to be the occupation ratio at the root. And it's been known actually already back since the 80s. Frank Kelly proved that P of h converges to a limit as h goes to infinity if and only if lambda is less than or equal to this critical value. So that's what the critical value is. It's where, when you take the deregular tree, the occupation value of the root converges. So as you get deeper and deeper and deeper, it doesn't matter, it converges. Okay. So we can already see that the complexity of evaluating this polynomial on arbitrary graphs depends on whether or not this thing converges. Okay, good. So I'm going to come back to that. But before I do, I'm going to give you two more examples of partition functions. And then with the kind of bigger set of examples, we'll be able to see what's driving what you can do and what you can't do. Okay, so the second example also comes from statistical physics, which is the Ising model, which again, we kind of brushed on yesterday. So in the Ising model, I've got two spins, which I'm going to call 0 and 1. And I've got a parameter, beta, which for now is going to be a real number. And it's associated with the temperature of the model, but it isn't the temperature physically, but let's just call it beta. And then what we're going to do is then when we have a graph, and I've gone to this tiny little graph here, a configuration assigns a spin to every vertex. So I've got to, let me move that thing. Oh, I don't know where it went. Anyway, so this configuration assigns spin 1 to 2 vertices and spin 0 to 1. And what happens is the spins interact along the edges of the graph. And so you get a factor of beta whenever they're the same. So here I've got spin 1 next to spin 1. That gives me a factor of beta. So this graph is weight of beta. I've denoted that by weight of the configuration sigma, W of sigma. And the partition function just says sum over every configuration. So every assignment of the Q is 2 spins. That should really be a 2, but it's going to be Q in a minute. So assign the spins to the vertices and then take their weight. So that's the partition function. Okay, and of course, we could compute the partition function for our little graph. So if we had a triangle, we could have all 1s, that has weight beta cubed. Similarly, all 0s has weight beta cubed. And the rest of the configurations have weight beta, and there's 6 of them, so we can write the partition function. And again, we could consider approximately computing the partition function, or we could consider sampling from the Gibbs distribution. So same thing. Okay, so now I can tell you generally what I mean by partition function, because I'm just going to generalize these 2 examples, actually with a sleight of hand, which you'll probably notice, but that's fine. So we're going to, in this talk, we're going to have a set of spins, which Q, which is going to just be the set of integers, 0 up to Q minus 1. So for the Ising model, we had Q equals 2. And in order to define the partition function, what I'm going to do is I'm going to fix a symmetric matrix, okay, which tells me how the spins interact with each other. So it's going to be a Q by Q matrix. So for the Ising model, I have a beta interaction on 0, 0, a beta interaction on 1, 1. The other interactions are 1. And then given a graph, a configuration just assigns a spin to every vertex. And what's its weight? Well, we multiply along all the edges of the graph of the interaction of the spins from the weight from the matrix, okay? And then the partition function, this is just strictly generalizing what we've done with Ising, just sums those up. So for example, we have the Ising model up there. If you heard of the Potts model in physics, it's just the matrix that has betas on the diagonal and 1s everywhere else, but there's Q spins. And independent sets is this little matrix here, because out gives you a weight, in gives you a weight 0. You can't have it. Everything else gives you a weight 1. That's what lambda equals 1, because I've taken a fixed lambda for that. Okay? So that's a generic partition function. And we're going to be interested now in general whether we can approximate these things. Okay. Last example, and that's because I want to give you the sort of 2 easy special cases where there are still open problems. And I want to give you this example to give you one. The last example I'm going to give you is graph homomorphism, because graph homomorphisms can also be captured in this partition function framework. So you probably know what a graph homomorphism is, but in case you don't, I'll just tell you. So I've drawn a graph G on the left and a graph H on the right. And for some reason, it's traditional to allow loops in H, but not in G. This is not important, so don't really worry about it. But what's a homomorphism? Homomorphism from G to H is just a map from the vertices of G to the vertices of H. And it has to have the property that you take every edge of G and map it to an edge of H. So we don't care what happens to non-edges, but edges have to go to edges. So for example, I've denoted the vertices of H by colors. Red is 0, blue 1, green 2. And then I've drawn a map from the vertices of the G to the vertices of H by coloring them 0, 1, or 2. And this map that I drew you is a homomorphism because if you look at any edge here, like the edge between 1 and 2, it is actually an edge over here. For example, if I took that top 1 and I colored it 2, it wouldn't be a homomorphism because green, green isn't an edge. Okay. So we can capture homomorphisms also in this framework quite easily. The way, sorry, this is a really cluttered slide. So I don't know, just look where I'm talking, I guess. So what we do is we take the graph H and we write down its adjacency matrix. So I've done that with A here. So if you look at H, the blue vertex 1 is adjacent to everything, and it's It's the middle row and column. And actually that accounts for all the edges. So this is the adjacency matrix. Okay, now let's go to our normal partition function framework. So what's a configuration? A configuration gives every vertex 0, 1, or 2. Okay, row or column of this matrix. What's its weight? Well, its weight is 1 if it's a homomorphism, if and only if it's a homomorphism, right? Because if you look at the adjacency matrix, a configuration will have weight 1. What do? We multiply over all the edges of the interaction in this matrix. And if you multiply with a 0, then it's 0. So the homomorphisms are exactly what counts here. And so the partition function is exactly the number of homomorphisms. And if you ever wonder why they called this field approximate counting, that's actually why, because you can count homomorphisms with these things. Okay, good. So that's the whole setup. Now, what I want to do next is I want to give you the theorems that are known for generic partition functions about exactly computing them, exactly evaluating them, okay? So everything good, set up, good? Okay, so let me tell you what's known. So there's the dichotomy theorem, which says that if I gave you a symmetric matrix A, then one of the following is always true. Either the corresponding partition function, or both, of course, if the world collapses, but the corresponding partition function can be computed in polynomial time, exactly, or else it's number p hard to compute. And moreover, if we look at the matrix, then we can tell which. Now, if you're not a complexity theorist, you might say, well, whatever, you've just said it's one thing or the other. This isn't true for free, because just as you know that if P and NP are different, then there's an infinite amount of stuff in between. Well, so similarly, if P and number P are different, there's an infinite amount of stuff in between. So it's by no means true that every computational counting problem is either in P or number P hard. That's just not true, provably. But for partition functions, it is true. So what that tells us via these theorems is that partition functions are particularly simple and nice. There's nothing exotic and weird and in between going on. And what this theorem also tells us is, given a matrix A, how do you tell whether its partition function is computable exactly or not? Okay, so this result came about slowly. So Dyer and Greenhill did 0, 1 matrices, and then Bulletin and Grohe generalized that to non-negative real algebraic. And then together with Grohe, Jerem, and Thurley, we generalized to real algebraic, and then Sai-Chen Liu to complex. I'm going to just tell you a little bit about the middle two. The idea is just to give you a feel for what does the criterion look like, what is the truth. And then we're going to move on to approximation, which was the actual point here. Okay, well, let's see when we can actually compute the partition function. So what I first want to tell you is what is the actual criterion when the matrix is non-negative and real. So I'm going to kind of tell you by example. Well, I'm going to tell you here, but let's look at this matrix A, just as an example. So here's a matrix. And I want to tell you whether or not you can compute the partition function corresponding to this matrix. And the first thing to observe is that it's useful to break the matrix up into blocks. And without defining blocks very rigorously, I just want to say a block is whatever stuff you get, connected by zeros outside. So there's a red block in the top left corner, and there's a green block and a blue block. And the way to think about that is you could think about the edge-weighted graph corresponding to the matrix. So 1, 0 has weight 3.5, and the rest of these edges have weight 1. And then if you have a connected component that's not bipartite, it gives you a block, like the red one up top. Or if you have a bipartite component, it gives you 2 blocks, like those 2 ones. Okay, so take the matrix, divide it into blocks. And now here's the criterion. So if the rank of every block is 1, then you can exactly compute the partition function. And otherwise, computing the partition function is number p hard. Okay, so this is kind of cool because it's a very simple criterion. So the truth is quite simple here. You can probably almost imagine why it's easy if the blocks all have rank 1. Because rank 1 blocks kind of mean everything factorizes nicely, and it's not very surprising or very hard to prove that you can compute the partition function in that case. But what was nice about these results was that they showed that for every other fixed matrix A that exists, it's actually number p hard. So that's the depth here, is that every other thing. Okay, so that's the truth for the non-negative case. And then I'm just going to briefly tell you the truth when the matrices can contain negative numbers. And the truth gets weird here. So I don't know, we're not supposed to like it when the truth gets weird, but I kind of like it because it is sort of strange. And so I'm just going to tell you what the criterion is. I'm going to tell you what is the criterion for a non-negative real matrix, symmetric, that would make it easy to compute the partition function. Okay, so roughly it's tractable if every block can be written in a particular way. So what's the particular way? Well, every block, for it to be a tractable matrix, should be a Hadamard product of a rank 1 matrix. So I've just drawn a little rank 1 matrix here, 2, 3, 4, 6, just to get us in the rank 1 matrix, with a Hadamard matrix. Now, what's a Hadamard matrix? A Hadamard matrix is a matrix, well, I'll tell you, it's a matrix of 1s and minus 1s. Actually, I've got that on the next slide, so we'll do that. But so first, what's the Hadamard product or the tensor product? It just copies, point-wise, so you can see 2, 3, 4, 6 goes up because it's a 1, 2, 3, 4, 6 negative there. So that's the product. Okay, so for the matrix to be partition function to be tractable, it should be decomposable into blocks. Each block should be written as writable as a rank 1 matrix tensor product with a Hadamard matrix. And a Hadamard matrix is not any matrix of 1s and minus 1s, but it has to be the case that when you multiply it by its transpose, you get a diagonal matrix. Okay, so that's already a criterion, but that's not the truth. The truth is that only some Hadamard matrices lead to tractability, and they have to have a kind of quadratic representation. So there's a kind of linear thing going on with this tensor product, and there's a quadratic thing in the background. So to get tractability, it has to be the case that the Hadamard matrix is represented quadratically in the sense that if you labeled the rows and columns over a field of size 2 to the k, and it will be 2 to the k because, well, anyway, it will. And then you can define a multivariate polynomial of the variables indexing the rows and columns, which is quadratic and tells you where the minus 1s are. So maybe that's all a bit weird, but what the truth says, if you take a matrix, I want to know whether the partition function be computed. It is if and only if it's an easy problem, if and only if for every block, you can decompose it as rank 1 times a Hadamard matrix, which happens to have this weird quadratic representation. So that's the truth. Okay, but enough about that, because in real life, we probably really want to approximate anyway. We probably don't want, I mean, we want to, but. Oh, is it testable efficiently? Yes, it is, but that's a really good question, and it's not right. Yeah, so we can tell. Good. Any more? Okay. And the easiest way to see that actually is later work. In fact, it's written down for the complex, but yeah. Okay. Okay, so now what I want to do is I want to go for approximating the partition function. And here, surprisingly easy things are open. So I'm going to be able to show you stuff that's super simple that we just don't even know. So it's actually kind of even embarrassing how much we don't know. Okay, so open even for very special cases. So we remember what approximation means in this F-press sense, or weaker if you feel like it. But even if A is a symmetric 0, 1 matrix, so you just want to count graph of homomorphisms, we don't know which ones are easy to approximate and which ones are hard. We know something about it, and I can tell you about that, but there are super easy cases where we still just don't know. So even the 0, 1 case is still open. The thing that I'm mainly going to talk about today is when the matrix is 2 by 2, and we still don't know. So it gets very much harder. So what I'm going to do now is I'm going to talk about the 2 by 2 case. So I've got my matrix A, but it's a 2 by 2 matrix. And since A is symmetric, I'm going to be able to normalize it to beta 1, 1 gamma, because if the off diagonals were 0, it's super easy to compute the partition function, right? You just beta component or gamma component, that's all there is. So I know these off diagonals are not 0 because I would have been done. And so I can divide by them, and I'll do this. And I've only got 2 parameters in play. So the weight of a configuration, every edge that's 0, 0 gives me a factor of beta. And every edge that's 1, 1 gives me a factor of gamma, and that's what there is. Okay, and now we're going to talk about this case, yeah? Okay, good. Okay, so we started considering this problem, which is not finished, back in 2003. And so this particular picture I stole from our 2003 paper. And it was the first scratching at the problem with Jerem and Patterson. And so what I've plotted for you here in this picture, so the beta axis is the horizontal axis and the gamma axis is vertical. Oh, there's nothing special about stopping at 3. I mean, it continues. But we divided the non-negative quadrant of beta and gamma into zones where you could approximate or not approximate. And the first thing we noticed in this paper is that above the hyperbola beta gamma equals 1, you can approximate. And the reason you can approximate up there is that you can actually, although you have 2 parameters, beta and gamma, you can kind of shuffle them around and reduce to the easing, which is beta equals gamma, together with putting a field on vertices. And a field on vertices is like the lambda of the independence polynomial, except for a different lambda for each vertex. But the important thing is that lambda would either always favor spin 1 or always spin 0, no mixing them up. And up there, it's therefore easy by reduction to easing, which was done by Jerem and Sinclair. Down in this bottom quadrant where beta and gamma are less than 1, it's hard. So unless NP equals RP, there's no polynomial time algorithm to approximate. And that's, again, an unsurprising result. And the way to think about it is if you look at the matrix, if beta and gamma were both smaller than 1, it means that any 2 vertices like to be different spins. And so you shouldn't be that surprised that with some mucking around in gadgetry that you can sort of simulate max cut and you can sort of make it hard. So the things that we expected were the bottom quadrant hard and the hyperbola beta gamma equals 1 easy. And the purpose of this little paper was that we sort of were surprised to discover that neither of those was the truth, because there's this curve going down, and there was another easy zone there, the ones that assay theorem 6.1 and 6.2, which I shall not tell you about. Those are more complicated Markov chain mixing results that get easiness. And then you probably can't even see, but there's this little glitch at the side of this square. And that's an area where we proved hardness. So what we noticed here was that neither of the natural things was true. Now, that was a long time ago. And since then, we know a lot more. In fact, we understand this whole quadrant. And so what I want to do next is tell you what is the true curve that separates easiness from hardness in this upper quadrant. Okay, so to do that, I'm going to go back to G delta, which is graphs of degree at most delta. And in order to state this, I just have to slightly generalize the Gibbs distribution so that it applies to infinite graphs, but that's not going to be anything very surprising. So the probability of, So a Gibbs distribution on an infinite graph just has the property that if you look at any finite region, then the conditional probability on that region is what you expect given the boundary. I think that's really all I want to say about it. Okay. So let's go back to uniqueness threshold, because we talked about this a little bit before. And it turns out to be true. And this is the same thing I was telling you before, but now in much more generality. And so we can understand it, is that let's look at the infinite delta regular tree. Okay, so let's just think about the infinite delta regular tree. So what kind of Gibbs measures do they have? Well, if it's in uniqueness, there's only one Gibbs measure, which is like saying that the marginal at the root, it doesn't really care about the height or anything like that, it converges. Or there might be multiple Gibbs measures. And the easiest way to think about this is go back to the independence polynomial and take lambda super, super, super big, so that you want big independent sets. Then there can be a parity effect because it's independent sets, so you can't have adjacent guys in. But if lambda is huge compared to delta, you'll want to have big independent sets. And so a lot of weight might be having odd levels in, or might be having even levels in, and you would get two different Gibbs measures. Okay, so what's going on is if in the infinite tree, if it's in non-uniqueness, so there's multiple Gibbs measures, then it's then be hard to approximate even on arbitrary graphs. But if it's in uniqueness for all d at most delta, then that was about the tree, but approximating works even on all delta regular graphs. Okay, now, how can you tell whether it's in uniqueness or not? I mean, it's an infinite tree. That's actually really easy, because what you have to do is you can write down the recursion of spins propagating up the tree, and we're going to get the vibe of it. So beta x plus 1, that's because if x is in, then you might be getting a beta, or 1, it's out, or vice versa. So we might look at the ratio of in versus out, and delta minus 1, because it's a delta regular tree. So what you do is you take this function, you find the unique positive fixed point, and if its derivative is less than 1 in absolute value, it's in uniqueness, and otherwise it's not. So that's something very easy to tell. And so the true threshold for whether you can approximate this polynomial or not in the upper quadrant is whether your partition function, whether you're in uniqueness for all degrees less than delta, your maximum degree. Now, the uniqueness threshold, annoyingly, the world isn't always so nice. It isn't monotonic in delta. And so the true curve, we don't have a closed form, because it could be in uniqueness for some d's and then not in uniqueness. The truth is the more disgusting. But so the true curve, therefore, if you don't care about the degree, is the in uniqueness for all delta. And that's just some messy function, but that's the thing. Okay, but there you go. And that we don't nicely know how to test, but yeah. Okay, so I promised you newer work. And okay, so that's everything I'm going to say about the top quadrant. So the top quadrant is done, modulo the fact that the curve, we don't have a nice closed form, probably doesn't exist, but we know the truth. Okay, so let's allow negative numbers again. And this picture is what we know about approximation in general. So this is, again, the beta gamma plane. And just to give you the punchline in advance, that white strip is actually just open. So that's the place where we don't even know whether you can approximate or not. And okay, but I'll just tell you about what we do know. So you can see the upper quadrant there. So we've just talked about that. You can see this beautiful little curve. That's just a cartoon of the uniqueness. I mean, it doesn't look like that. So this little dotted curve is in uniqueness for all delta. You can maybe see the dotted beta gamma equals 1 hyperbola. Okay, so what do I want to tell you about this? So these kind of blue points are the points where we know that you can exactly compute this partition function. And remember from earlier in the talk, we actually understand where you can exactly compute it. So those are precisely, there's 4 of them. You can see 1, 2, 3, 4 blue points. That's where you can just compute the thing. Oh, and on beta gamma equals 1. And beta equal gamma is the Ising model. And so we know you can do it up in the positive quadrant as long as beta is bigger than 1, and you can't do it when it's not. Now, if you go down into this pink zone, I actually have a much earlier paper with Mark Jaron, where we showed for Ising in the pink zone that not only can you not approximate the partition function of Ising, but actually even determining whether it's positive or negative is number p hard. So you take a value of beta sitting on that little strip, like maybe minus 1. And then if you could compute whether the partition function was positive or not, then you could actually, I mean, you could exactly count satisfying assignments and do whatever you like. So at first you think, oh, well, that's probably because you have to identify, it might be 0, right? It might be positive, it might be negative, and it might be 0. And probably it's hard to tell whether it's 0. But actually, it's neater than that. You could say, all right, my problem is telling whether it's positive, telling whether it's negative, and if it's 0, I just don't care. Say anything. And that's still number p complete. So hard. So so that's hard. And then this orange line, which is still a line segment, which is still Ising. In that earlier paper, we found that if you could estimate the Ising partition function on any point in the orange line segment, that's exactly equivalent to approximately counting perfect matchings in a general graph, which is a huge open problem in my community. We just don't know whether you can do it or not. But it turns out to be the same as approximating Ising in this negative zone. Okay, so that's that. Now, together with Yumufei and Pinyon Liu, the rest of this stuff, and what we've discovered is that if your beta plus gamma, if your absolute value of beta plus gamma is at least 2, then life is easy in the sense that in any of these green zones, there's a polynomial column approximation scheme for graphs of bounded degree, and also an FPRAS for arbitrary graphs. So life is as easy as you could want it. This blue line down here is just showing that as you get to that threshold, beta plus gamma equals -2, life is still easy for the FPRAS. The pink zone. The pink zone is where we can show for any point in the pink zone, if you could approximate any point in there, then you could solve all of number p exactly. So those are super, super hard to approximate. And then we get to the kind of truth in the fact that we don't have any nice bounds because there's a yellow strip. What's that there for? So the yellow strip is not a strip. It gets narrower and narrower as you move further out. But the point is that beta plus gamma is less than 2. So it tells us, so it's a zone where there is a polynomial, I don't know, I can't say that. There's an FPTAS. But beta plus gamma is actually less than 2. So this beta plus gamma equals 2 is not the true threshold because we can beat it everywhere just by decreasing amounts. And the other thing to confess is that if you go up in the top of that white zone, there are places we can prove hardness. We just couldn't prove anything nice. So probably if we knew what that curve looked like, the uniqueness for all delta curve, we kind of conjecture that if you extended that down, that's probably the true threshold. But since we don't have any closed form for it, I don't know. Okay. Right. So just a few minutes to say, how is it that we do this approximation? And in the old days in my field, every answer to this question is you take an appropriate Markov chain, you simulate it for a while, and you prove that actually you don't have to simulate it too long, and then you're sampling, and then you use the sampling to count. But for the FP-TAS, there's a different method. And actually, there's a few very new methods, but only one that I'm going to tell you today. So I want to talk first about the FP-TAS and how is it you approximate in these green zones in the bounded degree case, because it's a kind of neat trick due to Barvinok and Pato-Regs. And okay, so that's the theorem. If I take beta not equal to gamma, because we've already talked about beta equals gamma, and we're in the green zone, then there's an FPRAS and there's an FP-TAS. And so I want to talk about the FP-TAS. And to do that, I'm going to go all the way back to the beginning of the talk, and I'm going to put weights in just like the independence polynomial. So you remember for the independence polynomial, I had this parameter lambda, which I got a factor of lambda if a vertex was in. I'm going to soup up my partition function by putting such a thing back. So instead of the partition function as we had it, what I'm going to do is I'm going to take a vector x of vertex weight, let's just let it be real numbers. And for every vertex v, if sigma of v is 1, I'm going to give myself a factor of xv. Okay, so it's just a weight for putting v spin 1. So it's called the vector of external fields. Obviously, I'm interested in computing this thing at 1, 1, 1, 1, 1, 1, but it's going to be useful for me to have the flexibility. And obviously, if I put them all to some value x, then I get a single variable polynomial, which is what we want. Okay? Okay. So here's a cute trick which was noticed by Barvinok in 2016. And he's interested in when can you approximate single variate polynomials, and now we've got a single variate polynomial. And of course, you should think about the polynomial as having a zillion, well, you should think about d as being like 2 to the, no, d being n, but lot of d being 2 to the n, because we've got a lot of different terms here. And anyway, so what is Barvinok's idea? Barvinok's made the simple observation that actually, sometimes you can just truncate the Taylor series of the log of a thing. And whether you can do that or not depends on the zeros of the polynomial, but not over the reals. We better get back over the complexes. Even if you only care about reals, you should make it a complex polynomial. You should check its zeros. And then if it's zero-free, then the simple truncation of the Taylor polynomial is good. So this is what he's done. So he said, suppose that you have a disk of radius at least 1 around the origin. And what I'm going to do is I'm going to take the log of my polynomial. I'm going to call that f and fix some branch, fine. And then what I'm going to do is I'm going to truncate the Taylor expansion around x equals 0 at some point capital N. So that's here. And what Barvinok showed is that this approximation, as long as we don't have any zeros, then we don't have to make capital N very big to get an additively close approximation there. So in particular, it suffices to take capital N about the log of d. And of course, if the logarithm is additively close, that gives our polynomial multiplicatively close. So what we ought to do, if we want to work this way, is we ought to take our polynomial, we ought to think about everything over the complex. We ought to prove that there's a zero-free region, including the origin. And then we can take its log and truncate and so on. Okay, so that's the first step. Now, the second step, though, so we've got our polynomial, right, which is our partition function, which we've got 2 to the n terms. Log of 2 to the n, that's looking lovely. But if we're going to be doing this, we have to compute all the coefficients of this truncated Taylor series. And the second piece of the puzzle, which was done in really lovely generality by Pato and Regs, which is that they showed that you can compute the coefficients of this thing by reduction to counting induced subsets from certain graphs into G. So this is a really lovely generic trick. It works really well. And this is the whole reason, well, this is one of the reasons why we need bounded degree. One of the reasons why we looked at bounded degree is that the truth is along that bounded degree, like the critical point depends on the degree. And the second reason is that we don't even know how to compute these coefficients unless it's bounded degree. Okay, but supposing it is, then to get an FP-TAS, all we need to do is prove that there's no complex zeros in a disk in the complex plane. So that's what we do. And there's good techniques for looking for zeros of these polynomials. The one we use goes back to Asano in 1970. It's been well known in statistical physics. And it basically works like this. So here's our partition function. And I want to prove to you that there's a disk containing the origin that has no complex zeros. And what I do, just to kind of give you the kind of high level view, is we're going to look at this very simple polynomial. And where does this simple polynomial come from? Like if you look at the edge UV in this polynomial, what's the contribution of the edge UV? Well, if U and V both have spin 1, then I get a gamma. But if they both have spin 0, I get a beta. And otherwise, I get that. And so what we're going to do is we'll prove that this super simple polynomial has no zeros. That's nice because it's only got 2 variables, so we can look at it. And then this idea of contraction is that you just contract the variables for one edge into the next, and you just pay attention to what happens to the zeros. So you prove that there's no zeros for this edge and that edge, and then you contract the vertex. And working this way, you end up finding that there's no zeros of the generic partition function. Okay, so how do we prove that there's no zeros of the simple polynomial? Well, life turns out nice for us because let's look at this very simple polynomial here. Gamma xu xv plus xu plus xv plus beta. And let's just see what function of xu xv would have to have in order to make that 0. So I've written it as lambda x g of x plus g of x plus beta equals 0. And solve the thing, and lo and behold, you get a Mobius transformation. Nice. So now you say, okay, excellent, I'm in the complex plane. So the reals in infinity map to the reals in infinity. A circle centered around the origin maps to a circle centered around the origin. And all you have to do is check the real line inside the circle and see whether it goes in or out. And it goes out. So what it shows is that if x is in the disk, then g of x is not in the disk at 0. And so that works out. Okay, I believe it's time for me to stop. So what I will just say is that to get the F-pras, what you do instead, so that works, so this kind of like complex zeros gives you the deterministic approximation scheme when the degrees are bounded. When the degrees aren't bounded, we don't know how to do that, but we can still do an F-pras, and we do that by an appropriate Markov chain, but you have to kind of apply Fourier transforms and put the spins on the edges, but this works out. And then to show the hardness in this pink strip, what you do is essentially show that if you would fix a point in there, if you could estimate partition functions, then you could build gadgets where the partition function that arises from having a vertex in divided by having it out can realize pretty much any number you like, and actually that these things are dense in the plane. And once they're dense in the plane, you can use them to get hardness. Okay, and I'll stop there.
Hello? You turned it off. That's why.
Yeah, sorry.
Yeah, sorry. Questions for Leslie? See who was first?
Hopla. So if P equals NP, what is the implication on this, on the possible collapse of enumerative P-complete class?
Oh, if P equals NP, yeah, lots of things collapse, right? Because the hardness result, even in that square, is subject to NP not equal to RP, but NP would then be equal to RP. So yeah, I didn't keep saying it, but I'm always assuming P is not.
Because sometimes, for example, for 2SAT, it's easy to check if you have the solution, but counting the number of solutions, then it's hard.
Right.
So
Here's an interesting thing. I'm sorry, because I know I shouldn't answer at great length, but this is a kind of cool fact. So we have P and we have the polynomial hierarchy and we have number P way up there, and number P could be a whole lot harder. But approximate counting is never harder than NP. And that's because of this kind of cool hashing. You can always, anything in number P, you could approximate it with an oracle for NP. So if you give me P equals NP, then yeah, my life is worthless.
at some time, you had a list of extension of results with a non-negative, real algebraic constraints and so on. So why there was this hierarchy of succession of results? What is the difficulty which was needed to be solved to get to the next class?
Oh, okay. So, okay. So the question, if you didn't hear it, is why this results, what's the difficulty in getting from one to the next? And the first thing is to get, say, from non-negative reals to negative. With negative, you get cancellations. And the cancellations can make some things harder, but they can make some things easier because all the hard stuff just cancels, it's gone. And then what's left? On the other hand, with negatives, you can also do these binary searches and the truth is different. Like without negative numbers, you'll never get something that's number P hard for approximate counting. But with the negatives, you can. So the truth is just different. And I think we see that from the fact that the criterion is so different. Complex is not, I would say, so different to the negatives, except for the key insight that if you will focus narrowly on the real line, then you'll miss a whole lot of good tricks, which you maybe should have known, like looking whether there are zeros of polynomials and stuff. I mean, it took my community a long time to figure out that was what we should be looking for.
Other questions? I'll first come to you.
Oh, really?
It's a shorter route.
Okay. So thank you for a very informative talk. My sorry, my naive understanding of the interest in computing normalization constant is because they are good for MLE estimates, and also taking differentiation will give you moment information of the various statistics. So I was wondering, like, when you are just approximating them, like, is there any sensitivity issue with these things, or like?
Okay, good.
Yeah.
So the thing is that the approximation of these partition functions, because of this robustness, we can get within, 1 plus epsilon, 1 minus epsilon for any epsilon that you choose in time polynomial with epsilon. So why should you care? The reason you should care is that if you just want to sample with total variation distance, whatever, from the distribution, you can do it just as well with an approximation as with the exact value because the error just absorbs. So there's no real sensitivity there. So this notion of, another way to say it is that the notion of approximation is strong enough that it is the right notion if you're interested in qualitative things like samples. Yeah. Oh,
What
sorry.
happens if you want an approximation that is within a sublinear function of the value you're
A sublinear additive or additive? Yeah, so additive is quite, you must be additive, right? Because multiplicative, right, okay. Yeah, so additive is really different because these values can be quite large and often approximating additively. Yeah, I mean,
value over log value.
yeah. So there are some results like that, but not so many because they don't. It's not very robust. Like, yeah. Right. Yeah.
You get told off for skipping the queue, Ian.
Oh, sorry. I think that's
No,
wonderful.
there was a question here.
I have a question because in another community that I know, they are a bit interested in the so-called gap P complexity class, which is short P minus short P, something like this. And for approximation, does it give a much harder challenge, or would it be easier or something like this?
So for the exact results, gap P is super, oh, sorry, goodness. Gap P is super important for exact results. And there are some things that are complete for gap P and stuff like that. But for approximation, you can't subtract. So if you can approximate A and you can approximate B, you can't approximate A minus B. It's for the same reason why if you interpolate a polynomial and you approximate all the points, you'd learn nothing. And so, yeah, it's totally useless and it's really frustrating. So it's the reason why we don't know how to do some things, because there's a subtraction in there and all bets are off.
Okay, thank you.
Now that's going to be challenging.
We
We need one of those throw mics, but we could just pass it on.
When you're in the case that you have an efficient approximation like a FP-TAS or FP-RAS, do you know something on the degree of the polynomial or how efficiently it can be approximated?
So you want the actual polynomial?
Or at least the degree or something on how efficient it is?
Okay, so in general, I just have to confess that I don't remember. But actually, there's a whole thread in my field where we care massively about that. And then I'm just going to go back to the independence polynomial where we're mainly working. And there, you want n log n. That's what you want. And there's these cool techniques called spectral independence. And there you measure the effect of a spin on the spins far away. And yeah, the great thing to get is n log n, and sometimes we can get it, but usually not via just the Markov chain, or sometimes via the Markov chain, but with, yeah.
Are there more questions? Two more. Maybe we'll have to cut it off at some point.
Okay, thank you for the talk. So my question is, some of the models you showed us, they have corresponding like abstract polymer versions of them. And so approximating the genetic function translates to some kind of cluster expansion.
Mm-hmm.
So do the conditions you showed us in terms of the matrices translate to any kind of compatibility for the polymers?
So we use polymers to do, we can use the cluster expansion in the polymers to do better on the random cluster model.
Okay.
Okay, for example, or which is the top polynomial. So there are lots of polynomials where we know how to do that. The generic thing with the matrix, I don't think we have good results by polymers.
Okay, thank you.
Okay, last question. One more round of running.
Okay, so you advertised the approximate computation of the partition function in terms of sampling. And so the question is, for all of the questions that you've considered, is it the case that if you can approximate the partition function, you can do sampling by recursive reduction, basically?
Pretty much, yes. So pretty much what you can do is like, I mean, the best example, again, is the independence polynomial, because it's easy to pin a vertex in or out so that you can recurse. And in general, we do know such recursive methods, but it would be a lie to say always, because there are sometimes, but here, yes.
Okay, thanks.